All right, so as Romy said, my name is Jeff Wagner. I'm a researcher with D3R. Today, I'm going to be talking about our newest project called the Continuous Evaluation of Ligand Pose Prediction. And I think first the useful thing to do is to put this in English. And so this is just a weekly blinded challenge for pose prediction. We're starting this based on a lot of what we've learned from the D3R grand challenges. And the biggest thing is that there's a lot of people in the community who are willing to engage with us and give us time to help evaluate these methods, but that the way that we're doing it now, we kind of struggle to achieve statistical significance. And there's three big areas of this. One is that the community has been asking for more data, and this year you've seen that we provided more data, but the amount of work to curate that data, as Pat mentioned, sort of scales linearly with manpower, and we're limited on that. And so to get a bigger challenge, we want to move to a different format where manpower isn't so much of an issue. Also, Grand Challenge participants, they try very hard, and often part of their effort is having human input into their prediction workflow, which is great, and we're happy that people are willing to spend the time. But human input is often not reproducible. So we want to move towards something that evaluates more purely the algorithms behind it. And finally, when we see the best performers in grand challenges, we hope to learn a lot from their similarities, but oftentimes we end up comparing apples to oranges because these workflows are fundamentally different, or they use different numbers of steps. So we want to work around that. And the place where we started with CELPP was, we started thinking about the pipe dream of what if this problem was easy to solve, what would it look like? And one example of that would be if we have some sort of post-prediction workflow where we start with a protein structure in some unprepared format, we do some amount of structure pre-processing, and then just to single out one step, let's say that we care about doing protonation really well, then we might construct this workflow to use pro-pKa one time, and then we use the output from that to go and do some docking. The docking yields an RMSD, and then we go and we have this in a modular way where we can switch in a different protonation program, do the docking again, get a different RMSD, and then repeat for as many programs as we want to evaluate. So as I said, doing this once or doing this 10 times isn't going to tell us what is the best way to protonate and to prepare systems for docking. But if we find a way to do this thousands of times, then we'll start establishing sort of really significant data. So this started us looking for a source where we can get thousands of test cases for docking. And our colleagues at the Protein Data Bank have started doing something very helpful, which is that they release structures in batches every week. The new structures come out on Wednesdays. And 1 week prior, they announce information about which structures will be coming out. So we can set up a system to go and catch this data stream, analyze the complexes that are going to be released with their atomic coordinates next week, and then pick which of those we want to use for evaluating docking workflows. I'm going to go into the nitty-gritty of that a little bit. So here I'm showing in the gray box an example of the contents of this pre-release announcement. So this is a pre-release announcement for PDB code 5UGB. And on the first line, I'm showing the protein sequence, truncated because it's long. And then on the second line, another bit of information that they give is the identifiers for any ligands that are bound to the complex. So in this case, I'm showing the INCI, and it's kind of long, so I've truncated it. And we put together this conceptual workflow for what we want to do with this information to determine if this target should be used for the post-prediction challenge. So we start by downloading this data up above, and then we first look at the ligand. So we check this INCI string, and we basically want to make sure that it's interesting. We want to make sure that it's not a salt ion or just like a little solvent. We want to make sure that this is useful for evaluating docking programs for drug-like molecules. So we analyze and we make sure that the INCI string is interesting. And if it is interesting, then we move on to the next step, which is we take the protein sequence and we blast it against all the existing entries in the PDB to see if we already have a solved structure for this protein. And right now, this is a constraint in our filter. Right now, we're only doing things for which we already have one solved structure, and we're just trying to put a different ligand into it. In the future, we might relax this constraint, but for now, we're going to focus on cross-docking. So if there is at least one release structure, then we go ahead and we greenlight this upcoming entry. Then we start preparing the data that we're going to send out to CELPP participants. So we've done this blast search and we found any homologs of this protein that are already in the protein data bank. And from that list of search results, we pick models which should be easy to dock into, and also some models that should be hard to dock into. So we send up to 5 docking templates for each protein that we want people to, or each protein ligand complex that we want people to predict. The number of targets that end up making it all the way through the filter and getting the green light each week generally ranges from 20 to, on the larger end, 100, and those will be if a structure series comes out. So those aren't necessarily totally unique. And again, because we send out up to 5 docking candidates for each upcoming release, this could mean that a workflow has to run up to 500 docking jobs in the time allotted. For those who have been following our Twitter, you'll see that we've actually been talking about CELPP for a while. So we had this workflow thought up last year, and we've been implementing it and actually running it for 40 weeks. The thing that we started with was implementing some common docking workflows ourselves. So things like AutoDoc-FINA and Glide and OpenEyeFred. We just made very basic workflows that would go through and do post predictions using those software ecosystems. On the hosting the challenge side, most weeks everything runs completely perfectly automated. The PDB pre-release file is downloaded, the blast search is done automatically, the files for the participants are put up online where they can download and start making their predictions, and then these submissions are collected and evaluated at the end of the week. And one of the great things is that members of the community came forward to volunteer and be sort of our beta testers while we worked through a lot of the problems and a lot of the bugs in the infrastructure. And we've actually gotten a decent throughput of data and predictions from them that have been submitted. And here's a summary of what we've received. This is data aggregated over the last 40 weeks. I'll walk through this table. In the first column, we have the different methods that are making predictions. All of the public participants are currently anonymous because we have bugs on our end and they're probably improving their workflow, so we don't want to commit anyone to their results. The workflows that we made internally are tagged with D3R, and we've named them here. And I've sorted this by this first column, and this is sort of the curse of Greg, I suppose, which is the metric being what fraction of the submissions from each of these prediction workflows comes within 2 angstroms of the crystal ligand. So we're sorted by descending order in the second column, but it's worth noting that if we look at the predictions and we take the median RMSD of each prediction server or the mean, that we get a slightly different order. So this isn't necessarily set in stone. Also, I include this last column. So these prediction workflows are free to not predict for any protein ligand complex. And you see that there is a variation in the number of submissions that each one makes. And this is due to the different amount of time that these servers have been running and making weekly predictions, and also sometimes the pickiness in how they'll prepare structures or what sort of protein motifs that the program will accept. 2 angstroms here is a sort of arbitrary measure. And so we can look at the data also for a range of different cutoffs. So these plots are showing RMSD on the x-axis, and then the fraction of submissions that come in under that RMSD on the y-axis. Each different line is a different prediction method. All the colored ones are the internal D3R ones that we've named. The black are all anonymous participants. And we find the same numbers as we had seen on the table. So for example, if we look at the best participant from this table, this family is getting it right about 20 to 26% of the time, right as in within 2 angstroms of the crystal. And we get that same number by looking at the 2 angstrom RMSD line here, and then just finding where it intercepts each curve and getting the Y value. So for a different range, we can see that sort of there's a cluster of best performing algorithms, but that they all sort of follow this curve. Before, I had told you that we send out multiple docking templates for each prediction. And I'm only showing you 1/5 of the data here. So this is a docking template that's supposed to be the easiest. We do the blast search, and then of the results from that blast search, we pick a docking template that has the most similar ligand to the unknown. We're also kind of jerks, and we send out a really hard docking template too. If available, we'll go ahead and find an apo structure for the same protein. So this is the same proteins that we're looking at, just a harder docking case. And now all of these curves have shifted downwards. So if we take the same metric, looking at what fraction of submissions come in at 2 angstroms RMSD or less, now we're more like 10%. And this is sort of cool. This is the first time we've looked at data coming out of CELPP, now that we have a lot of it. And it's nice to see something that's sort of common sense, but that's being reflected in the numbers. So if we put these side by side, now we can make sort of a useful big picture generalization, which is that if you have a good arrangement of your binding site, if you have your protein and your docking template is bound to a similar ligand to the one that you're working with or the one that you're trying to predict, you'll have an improvement in your odds of getting a good RMSD as opposed to using maybe a misarranged binding site. So I hope everyone's really excited about CELPP. We want to get more people involved. So at this point, the talk turns into a sales pitch. We want people to join. And you can do that by Googling CELPP, and you'll find your way to the wiki that we host with our GitHub with all of our code. We have a big instruction set for how to participate in the challenge. If you just go ahead and click on that blue link, and you can come by my poster or talk to me at lunch if you're interested in getting URLs for all of these. Making a workflow can be kind of intimidating, and to make it less intimidating, I have a video where you can listen to my annoying voice for 17.5 minutes, and also a written tutorial that documents how we put together an Autodoc Vina workflow. And it's very bare bones, but it walks through sort of what we would do on the command line, just starting with a named ligand file and a protein file and ending with a prediction, and then how we put that into an automated workflow that submits to CELPP every week. Also, one sort of quiet theme of this conference has been that containerization is good, and it makes your methods more portable in a lot of cases. And that's something, especially looking at the modular nature of prediction, how maybe we want to do docking using the same algorithm, but we want to swap in a different protein preparation or ligand preparation algorithm. Having each of these preparation steps in a container will make it really easy to mix and match and plug and play workflows to put in potential improvements and evaluate how they do. Moving forward from today, we're putting as our first goal, engaging the community more. So we want to gain more participants. And so hopefully today you'll want to come sign up. We're also looking at better ways of sharing the results. Right now, we're thinking about a file format, maybe like a pandas data frame, as well as an online visualization like we have for the grand challenges. Because a lot of what we talk about here is about different evaluation metrics and enabling people to do their own evaluation of what works. As I said, we want to enable better sharing of methods. So basically do containerization either of entire prediction workflows or of individual steps so people can mix and match. And we're also looking to reach out, or we have reached out to MolSI and Biosim space, who are also working in sort of this discretization of molecular modeling space and improving the quality of software. In the future, we also want to enrich the results data set. So for instance, we saw the difference between using the best available docking template and the worst available docking template for a protein. But there's much more detail that we could go into. We could say, well, how similar was the ligand from this best docking template? Because sometimes it'll be really good, maybe even identical, and sometimes it'll be really bad. We could also enrich the pandas data frame with information like how many torsions the molecule has. And so we could maybe identify a docking program that's better for flexible or non-flexible molecules, as well as classifying some aspects of the pocket and seeing which preparation or docking programs work best for those. And also, as with D3R, we always have an ongoing discussion of evaluation, and in an automated way, we can start plugging that in as well. On a nice note, looking at the numbers, we're on pace to come near 1,000 targets in this first year, even despite the any bugs or trouble running that we've had. So this is good, and we're generating a lot of data, and we're going to be able to make conclusions from this. And finally, we're thinking about moving towards predictions of other properties. So for example, affinity or things like that. We have this infrastructure and people are registered and automating submissions. So this would be a really neat direction that we're looking at in the future. With that, I want to thank the entire CELPP team. That's been Chris Juris, who helps with a lot of programming, and Mike Chu, who's been working on the website. A couple alumni, Vicky Faher, Shwai, who's here today, and Rob Swift, coded a lot of the stuff before I got here. And also Romy Amaro and Mike Gilson, also D3R, the protein data bank, who have helped us a lot with these pre-release and answering questions promptly when we have any problems. And of course the NIH. Thanks.
Okay, questions today?
This is really, really cool. But it seems like you had this tremendous opportunity now to start debugging these methods, right? To try to figure out, you know, it's disappointing. You're only getting like 22%, right? Within questions. So, you know, what's your plan for trying to figure out whether there's some systematic things that are going wrong and how we can use this to make the methods better?
That's a good question, and I'll answer it in two ways. So one is that we want people from the community to come in and put in their solutions to these problems, because we, you know, like our manpower doesn't scale. We don't want to be testing all of the solutions. As people make new algorithms that can potentially solve things, we hope that they'll come forward and make a prediction server that will get better results. I'm sorry, could you repeat your question? I had a second thing.
What are you going to do to try to figure out where things are going wrong? Because I think that's really important. I don't know. So do you make all of the individual predictions available, as well as even the structures that are generated by these programs? A lot of data, but it could be incredibly valuable.
Yeah, we are. So we want to talk to our participants about specifically how they will be identified and how we're going to handle anonymity. So in a grand challenge, for instance, everybody gets an ID and it's sort of a one-shot thing. And if you choose to reveal your ID, then that's fine. You know, but if you choose to remain anonymous, that's also fine. With CELPP, because this is a weekly thing and people are going to be submitting week after week, and we want to track which workflow made what, if somebody gets outed once, or if some aspect of their predictions reveals which program they are or which company they are, then their anonymity is gone forever. And so this is something that we need to talk about with the community and with the participants for if we're going to release exact poses or aggregate metrics and what options are going to be available.
So Jeff, very quickly, are you thinking about, one of the things that we look at is that docking performance is correlated to, if you will, the quality of the structure. The simplest quality of the structure is how much electron density is there for the ligand, or how much electron density is there for the active site. And, you know, what you're seeing, and we can actually correlate exactly that the performance is better when you have higher quality structures. Whether or not that's because they're more rigid or whatever, it's not clear. But the higher, you know, the more complete the data for the structure, the more likely the docking program is to be successful. So is there any plans on giving us some hint of the quality of the structure, either pre or post, so that we can figure out why things are going good or bad, versus forcing us to do that? And again, if you need help with that, ask, because we have to spend time doing it.
That's great. Thank you for the offer. And I'll say that right now, I sort of glossed over a lot of the technical details, but what does get sent out, which with each prediction folder for every upcoming target, is a summary of which structures we chose for the docking. And these structures are chosen primarily on the basis of, for example, like ligand overlap, if we're looking for an easy one. But then we've also aggregated information about the crystallographic resolution, and that's included in the data package. So this is something that both the participants will know when they're making their predictions, and also it's something that we can attach to all of their results at the end of the day. So on two levels, both the participants can maybe change up their algorithm to deal with wobblier binding sites. And also when we do our analysis, we can see if there is a correlation between performance and crystal resolution.
This is a very exciting thing that's been a long time, so thank you for doing this. You know, the way central participants use central often is to submit a variety of predictions with different methods where we want to go. And they get very few shots at it because it only comes out once a year or twice a year. With this, you can do A/B testing. So do you imagine it's going to be easy for, or how can you make it easy for people to try multiple different variants and keep adapting them on the fly?
Yeah, that's a great question. It's difficult, and the way that would work the best is if, whenever possible, people put their workflows into containers. And I think that it would be good on either level. If people put their entire workflow in a container, then that's fine, because somebody else wouldn't have software compatibility issues when they bring it onto their computer and go and change some code or change some logic. But even better would be if people took their individual steps, their protein preparation, their ligand preparation, and their docking, They put those into containers and they sort of accepted a common interchangeable file format, something very informative like mol2 or SVF, where yeah, you could really plug and play a different way to prepare a ligand and still come up with good A/B testing at the end.
Just real quick, I think we may have more of an answer than you think, because you currently have a tool to allow one participant to have multiple methods, but they can be running in parallel. You could be running any number, so people could be hacking.
Yeah, this is a great discussion.
Yeah.
But we're already over, and we have time at the end to talk just about this stuff. So